Very few molecules are rigid. The theory community has been stuck on rigid molecules for a long time, and real molecules may contain tens of conformers, hundreds, maybe thousands of conformers, and the only way to get properties of those molecules is to begin to average those conformations. This is not a trivial problem. The first thing you have to know is what's known about molecular conformations. And there's a great deal known. In the gas phase and in solution also, there may be 100 or 200 small molecules where we have known conformations. In other words, we actually know the shape. In the crystal, although you have to worry about crystal packing, there are 500,000 molecules that are flexible, and we know the conformation. So we know a great deal about shapes in crystalline forms, and we know a smaller amount about conformational preferences in isolated molecules or in solutions. Good calculations are available for perhaps 100 molecules where you have some conformational flexibility, but only a couple of molecules where you have multiple degrees of conformational freedom. There's very little data there. The more difficult question is, what do we know about the energetics of alternative structures? We see a molecule in a given structure. What do we know about the next structures up? And the answer is almost nothing. There's nothing known from X-ray diffraction. You only see one crystal structure. Very rarely do you see two. In the gas phase, experimentally, there are a few molecules, maybe 50, where with 1 degree of freedom, things like N-butane, where you know the difference in energy between the good one and the next one. So there's relatively few data. From calculation, we have, again, a few molecules where we know the difference between the good one and the next one. And we have a few molecules, very few, 3 or 4, where we have multiple degrees of freedom, and we actually have good calculations relating to them. The most complicated of those molecules is melatonin. Melatonin is very simple. 2, 3, 4, it's got 5 degrees of freedom, and there are about 50 or 60 conformers in it. And if you look at reference, which is couple cluster theory, very expensive calculations, versus something really simple like mechanics, which is what everyone does for conformational analysis, it's not quite a scatter plot, but it's pretty bad. And I can't really say if this generalizes to every molecule because we don't really have very many molecules. But I can say that the work that's been done is that mechanics. You now go to B3-LIP, the simplest of the density functional models with a big basis set. It's not very good. And so what we're saying here is that people have been putting a lot of faith in these old functionals, and they're really not very good. It's better than mechanics, but it's not very good. However, the positive lesson is if you go to some of the modern functionals, this is XV, this is looking at energy differences, the reference, what we believe is really quite close to exact, versus this one, it's really quite excellent. So what we're saying is that density functional theory can, properly applied, can get good data. Now that methodology is too complicated. We can't really use this method, even though these are just energies, we can't really use this on molecules that have 1,000 conformers. And so we have to try to do some simplifications. The first simplification is that we're going to take this giant base set and replace it by something more manageable. Technically, I'm actually doing something a little bit more than that, but let me not worry about that. The second simplification is that we really can't do those calculations on 1,000 objects. We really have to find some way of simplifying. And so I'm going to introduce not an approximation, but a recipe. And that recipe is the following. It looks frightening, but it's actually very simple. It says, take some object, 1,000 conformers, and do a mechanics search with a very large error limit. What I really want to do is simply get rid of the very bad ones, and mechanics is good enough to do that. Then give me some very inexpensive structures of those molecules, and I'm going to use Hartree-Fock theory. I said Hartree-Fock theory has some uses, and I'm going to use that to give me my first set of structures. I'm going to do a simple density functional theory to give me a better guess initial guess at energies. Every step along the way, we can remove conference because we can slowly tighten our criteria. I then say, okay, we now have energies at not very good structures, or let's now get very good structures, and now let's get very good energies. So in a 5-step procedure, we can hopefully get the same result that if we just did this directly. Let me give you an example here. Just a couple of simple natural products. I didn't want to draw anything bigger. This thing has 24 conformers, not very complicated. If you were to do this directly, you'd have to do 24 calculations, not that many. If you doify the recipe, you'll end up only having to do 3 conformations, and you get the same answer. Another one is a little more complicated. This has 1 rotatable single bond and then 5 bonds in rings that are constrained. There are 324 possible conformers. If you want to do 324 calculations, that's a lot worse than doing that simple recipe, which would actually end up having you only have to do 4, and you get the same answer. Okay, let me end with one topic. The place you can prove that you're actually learning something about the structures of flexible molecules is to do an experiment which is an average over flexible molecules, and that's NMR. And we did an interesting experiment which will land up in a paper that's going to insult a lot of natural products groups. We say, look, we have a protocol. You draw a molecule. You take this protocol I just gave you, which is how do you get the weights of the conformers, Boltzmann weights, their relative energies. You now say, well, how many ever I have, I calculate the individual spectrum for each. I multiply the two together and I get a final spectrum. We did a test of that on a set of structures where we actually knew the result. They're the blue bars on this curve. This is a set of, it's about 900 now, natural products where we actually knew what the conformation was in the crystal. And we calculated the NMR spectra of that and compared it to the experimental one. And you get a fairly clean distribution there. The worst outliers, this is overall RMS error, worst outliers are something like 4 ppm, which is acceptable. There really are no bad ones beyond that. And then what we did is we now took a collection of, it's about 1,700 molecules now, which do not have crystal structures. And we made the same plot. Those are the red bars. And what you see here is that the distribution is one, it's shifted. And secondly, there are about 10% outliers. Those are incorrectly assigned structures. And one can argue that, but I think the evidence now is pretty strong that the theory is what it's doing is it's not telling you what the right structure is. It's simply saying that given my calibration with things where I actually know what the conformation is, what I know what the conformation is, or structure is, when I apply that to molecules where I don't have X-ray crystallography, where I've simply obtained the structure based on NMR evidence, I can clearly point to their problems. Okay, I'm gonna wrap up here. What I've tried to do here, and it's a little bit haphazard, I apologize for that. I've sort of given a sort of a very brief overview of a course we give rather frequently, which is several days. Just trying to touch on a few topics. I'm happy to make notes of that available to anyone, but this is a big field, and there are places which are very much missing, and there are places which are pretty well developed now. Okay, let me stop there. Thank you.